Black holes haunt our universe. Dark centers of gravity that swallow everything in their path. What would you see if you got close and fell past the point of no return into a netherworld of twisted space and time? What secrets can we learn about the universe on a journey to the center of a monster black hole? Imagine traveling to the very center of our galaxy, 26,000 light years away, and finding a vantage point on the night sky. You'd see millions of stars, and on the horizon, a strange dark sphere rising. It's a black hole, an object so dense, nothing can escape its gravitational pull, not even light. This monster is 10 times the size of our sun, yet millions of times heavier. It's not the only one out there. In nearly every large galaxy, astronomers have found evidence of black holes, millions, even billions of times the mass of the sun. How did they form? And how did they get so large? In the search for answers, we are beginning to glimpse the forces that shape the stars, planets, even life. And now, by tracing the life cycle of black holes, scientists are finding clues to the fate that awaits our galaxy and the universe at large. But how do you study something that by nature evades detection? Sometimes the universe lets us in on its most mysterious workings. March 19th, 2008. Astronomers around the world receive an alert sent from an orbiting observatory called SWIFT. It had recorded a flash of gamma radiation, a kind of ultra-high energy light that is the signature of a cataclysmic event. SWIFT automatically relayed the information down to Earth. And within seconds, robotic telescopes in North and South America turn their gaze on the rising light. Astronomers dial into the data to see how bright and powerful the flash had become. Meanwhile, at giant observatories in Chile and in Texas, they zero in on it, using specialized instruments to split the light into all its different wavelengths. That tells them how far the light had traveled to reach Earth. What they find is that it had come from 7.5 billion light years away, halfway across the visible universe. Tom Vestrand heads a robotic telescope project at the Los Alamos National Lab in New Mexico. He has been tracking high-energy gamma-ray bursts for over a decade and has never seen anything like this.
Okay, let's see what we have. It was the most luminous thing ever detected by mankind. Traditionally, think of astronomy as something that happens very slowly. But this was a thing that had been traveling to us for 7.5 billion years, arrived here, and for 30 seconds, it was astonishingly bright. amazingly bright minutes later, even still showing signs of saturation.
Yep.
It was so bright, in fact, that it was visible to the naked eye. Putting together evidence from ground and space telescopes, astronomers determined that the flash was a narrow but intense beam of light, and that most likely it broadcast the birth of a black hole. This singular moment is the endpoint of a violent chain of events in the core of a large star. All stars shine by burning light elements like hydrogen. In the largest ones, intense heat fuses these elements into heavier ones, like carbon, silicon, and finally iron. Like hot air in a balloon, heat and light from these nuclear fires creates an outward pressure that prevents the star's massive outer layers from collapsing inward.
Eventually that fuel runs out, the energy flows out through the star off into space. It can't go on forever. When the fuel runs out, the star starts to shrink.
And when that iron core builds up to about 1.4 times the mass of the Sun, it can no longer hold itself up against the pressure and it will collapse.
In some cases, as matter slams into the star's core, the impact creates a powerful shock wave that races back out and literally blows the star apart. Our galaxy is littered with the scattered remains of these supernovae, as shown in images like these from the Hubble Space Telescope. But what happens to the collapsed core of these dead stars? When a large star implodes, its weight is enough to squash all the atoms in its core down to their nuclei. The result, an ultra-dense ember called a neutron star.
The density of a neutron star is something like taking a mountain and crushing it down to the size of a marble, about so big.
Neutrons can withstand incredible pressures. But if enough matter falls onto them, beyond a critical threshold, they can be crushed down to nothing. When that happens, a black hole is born. A black hole is gravity taken to the extreme. Its mass is literally packed into a point and enshrouded within a dark sphere called the event horizon. That sphere is the point of no return. Any gas, stars, or planets that fall in disappear forever.
A black hole is a region of space and time which is both black and empty. It's black because light can't escape from it, gravity pulls the light back, but it's empty because the object or system that collapsed to form it in the first place has shriveled away to nothing.
The common idea that a black hole is just made of very compacted matter, it's wrong. It's just simply wrong. It may have been created from very compacted matter, but the matter is gone. It's been completely destroyed. It no longer exists.
And yet it leaves behind a powerful legacy, its gravity. According to Albert Einstein, gravity is not just the attractive force of planets and suns. It's a warping of space and time, what scientists call space-time, in the presence of massive objects. A planet, for example, goes into orbit when it's caught in the warped space surrounding a star, like a ball spinning around a roulette wheel. With the mass of a star squashed down to a point, a black hole is a deep puncture in space-time.
when a black hole is born, the energy gets transformed from the energy of the matter to the energy of warped space-time. So it's a transformation of the form of the energy from one to another, but the energy is still conserved. What you're left behind with is warped space-time that has a huge amount of energy in it.
With that energy, a black hole can affect its environment in profound ways. On our planet Earth, we know gravity as the force that brings everything down. The impact releases energy, a crash. A thud. A shatter. When matter falls toward a black hole, the energy released can reach astronomical proportions.
When we look at how they affect the rest of the universe, we look at what happens around them, what happens when stuff exploits this huge gravitational potential, this huge gravitational hole that they form, and how that is exploited to make energy.
Such energy emissions are part of a growing body of evidence that black holes, famous for hiding in the dark, have a history of outbursts that have reached across the cosmos and shaped the universe we know. Scientists are following this energy like a trail of clues, leading ever closer to the black hole's dark heart. Astronomers once saw black holes as rare and exotic in a universe seemingly dominated by stars and galaxies. A radically new view has emerged from surveys of galaxies and black holes stretching deep into the universe. Giant black holes lurk in the dust lanes and swirling gas clouds at the centers of nearly every large galaxy. What's more, the larger the galaxy, the larger the black hole. That's a clue that they must have evolved hand in hand, each shaping the life story of the other. To find out the role black holes played in the evolution of the universe, astronomers are trying to recreate this shared history with what amounts to a whole new branch of science. They are using supercomputers to simulate the sweep of cosmic history, including that of galaxies like our own. This simulation takes us back to just a few 100 million years after the beginning of the universe. Gravity drew vast pockets of gas into dense centers. They grew hotter and hotter, igniting to become the first generation of stars. These stars lived hot and fast, and in only a few million years, some blew up in powerful supernovae. From these stars likely came the first generation of black holes. Cosmologist Tiziana Di Matteo is part of a wider effort to see what marked these early black holes left on the universe. Her computer program simulates the action of gravity on gas, the formation of stars, galaxies, and black holes. Her goal is to create a virtual universe that evolves like the real one did, with black holes and galaxies emerging and growing together. Our Milky Way galaxy is located in a quiet part of the universe, with relatively few other galaxies around it. Move out across the cosmic void, 50 million light-years away, and you encounter the Great Virgo Cluster, filled with thousands of galaxies. Recent telescope surveys show that this region is part of a larger pattern of galaxies resembling a vast spider's web. To get her virtual universe to look like this, Tiziana needs to know what cosmic conditions gave rise to black holes and galaxies in the first place.
So it's a beautiful problem because we start from extremely well-specified initial conditions. We know the initial condition of the universe, and that's very rare in astrophysics, in cosmology, in any branch of physics.
Details of what the universe was like in its earliest times have come courtesy of a breakthrough observatory called WMAP. It found a blotchy pattern in a kind of radiation generated soon after the Big Bang. Astronomers believe this pattern is the origin of the spider's web structure they see in their telescopes. It defines the beginning point of Tiziana's simulation. She sets her virtual universe in motion. It covers a region in the shape of a cube over 100 million light-years on a side. The result, an intricate cosmic web with gravity drawing matter into filaments and knots on the largest of scales. In places where filaments come together, galaxies and black holes first begin to appear.
All the matter that is coming in from the large scale will also allow the black hole to grow because of these gases being transported from large scale all the way into the galaxy, and the galaxy all the way into the center, and therefore feeding and growing these central black holes at a very high rate.
In this sequence drawn from her simulation, the circles indicate the appearance of black holes within the data. What she finds is that as these black holes gain mass, gravity pulls them toward the densest regions, where a few grow larger than all the rest. How did these chosen few black holes grow so rapidly? The orbiting Chandra X-ray Observatory recently turned up evidence at the centers of galaxies back in the time of the early universe. These images show its remarkable find, actual supermassive black hole pairs, beginning what astronomers believe is a dance of death. In most cases, their forward momentum simply causes them to go into orbit around each other, like a planet around a sun. This orbit can go on for billions of years. To grow large, one black hole must draw the other in, close enough to swallow it. Albert Einstein showed how they do it. He predicted that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. It's like a rock hitting a pond. Some of the energy of the impact is transferred to waves that move outward along the surface. Likewise, a titanic collision of black holes would send waves, gravity waves, racing across the universe.
So you have two tornadoes embedded in a third larger tornado, and they're going to come crashing together, and you want to know what happens when these tornadoes are not made from whirling air, but made from whirling warped space and time.
This simulation shows what happens. As two black holes get close, they turn space into a turbulent sea of gravity waves. These waves have the effect of carrying energy away from the orbit itself. That allows the pair to draw each other in and merge into one.
we go back to half of the age of the universe, and all of these black holes are swallowing large amounts of gas. So it's a fun time. It's sort of the golden age for the growth of most black holes. The reason why is because most of the large major mergers are occurring in the universe around this time.
This simulation shows how a galaxy like our own might have taken shape in a flurry of mergers and collisions. In the beginning, gravity drew patches of stars and gas together. A new, larger patch drew still others. In fact, the universe is littered with galaxies in the process of ripping each other apart and crashing together. In the turmoil of each new merger, another victim is thrust into the jaws of a growing black hole. And in the densest regions of the universe, a small percentage of these monsters have been able to grow to a level of size and ferocity we can scarcely imagine. And yet, amid all the violence, are clues to how the universe, and even places like Earth, came to be what they are. Astronomers have long puzzled over a class of ultra-bright beacons of light from the distant universe called quasars. In time, they link them to the outpouring of energy from the centers of galaxies and to growing black holes. But how can something that emits no light shine so brightly?
2 minutes.
The chance to solve this mystery has drawn a crowd near NASA's Kennedy Space Center in Florida.
80 seconds. Rangers go.
45 seconds.
Mounted in the nose of a rocket just up the beach is the next generation cosmic explorer.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go.
0. Liftoff. Delta rocket carrying blast. Gamma ray telescope searching.
The Fermi Gamma Ray Space Telescope is part of a larger effort to explore the role black holes play in shaping the universe.
Farewell. Catch on the other side. Yeah.
To me, the idea that we're standing here on this planet in our own little area of our galaxy, we're able to look around and make meaningful measurements, have a theoretical understanding of the entire universe in which we live, to me is something that all of humankind can justifiably take pride in.
The black holes that interest Steve Ritz, a project scientist, and his team are among the largest ones out there. The energy they emit is thought to stem from periods of rapid growth at the center of galactic feeding frenzies. Billions of years ago, in places where the universe was dense with matter, gravity drew swarms of young galaxies hurtling toward each other. A large galaxy grew in the center, and when another galaxy fell toward it, it hurled matter at a central black hole. Force-fed like this, the black hole could grow up to several billion times the size of our own sun. Probing the Perseus Galaxy cluster, the Chandra X-ray Observatory found immense hot cavities hollowed out of the surrounding gas. The culprit, they believe, is a jet of radiation coming from a large central galaxy. As it roared out, this jet created shock waves so powerful it pushed huge volumes of gas beyond the central region. And without this gas, new stars can't form. That explains why some of the largest galaxies are filled with old stars, most likely born before their black holes began erupting. At the same time, a black hole jet can seed the surrounding regions with the heavy elements needed to form solar systems and planets like ours.
The black hole also has the property that as it spins on its axis, as the Earth spins, it drags space into a whirling motion like the air in a tornado, faster near the horizon, slower farther away, just as the air in a tornado is whirling faster near the core than it is farther away.
In the eye of this cosmic tornado, gas and stars flow into the hole along a rapidly spinning disk. The spinning motion generates magnetic fields that twist around as matter swirls in. These fields channel some of the inflowing matter out into a pair of high-energy jets.
So we can extract then the rotational energy of a black hole. Nature can extract it. And the amount of energy you get out is enormously larger than all the energy you can get from burning all the nuclear fuel inside of stars.
It's the equations of Albert Einstein that describe the source of this incredible power, the extreme warping of space just outside the black hole. What we can learn from these equations doesn't stop at the event horizon. They can also let us enter, with our minds, the realm within a black hole. Most likely, we'll never directly see how those equations play out and live to tell. A future explorer prospecting for data would tempt fate by traveling too close. If the monster is a collapsed star, weighing a few times the mass of the sun, its gravity rises sharply. The pull on the starship's nose is so much greater than on its tail that gravity rips it to shreds. Ironically, you'd find a gentler ride into a supermassive black hole. Its larger size means its gravity is more spread out. What you'd find if you made it inside is the most extreme destination in all the universe. Andrew Hamilton, an astrophysics professor, has been investigating what happens when matter falls inside a black hole. Using Einstein's equations, he and other scientists believe that falling into a black hole is equivalent to moving down a river and tumbling over a waterfall. Like a cosmic precipice, the outermost region of the black hole, the event horizon, is where space itself flows relentlessly in.
What does one mean by space falling or doing anything? It's just that if you put objects in space, then they will move in certain ways. And if you put objects near a black hole, as they approach the horizon, inevitably they must approach the speed of light in order to stay at rest. Otherwise, they're going to fall inside the horizon.
If the black hole is spinning, the central region is bounded by what's known as the inner horizon. In a case defined only by Einstein's equations, an object may whip around so fast it gets flung outward.
If there's nothing inside the black hole except the space-time structure itself, well, there's nothing inconsistent about having space fall inside, turn back around and come back out again, because space has no substance, so there's no problem with it moving through itself.
It would be like a river racing over the falls, hitting the rocks below, then flowing back up.
In the strange world of general relativity, you fall in through a region, a black hole region, where space was falling faster than light. And now space has turned around and is now pushing you outward faster than light.
Imagine charting a starship's course into this topsy-turvy realm. If you survived the fall down to the event horizon, you'd accelerate through it.
You go with the flow, you hit the speed of light at the horizon. Now, you can still see stuff from the outside world, even when you're inside the horizon, but people can't see you because space is falling faster than light.
To understand the chaotic region within, Hamilton has enlisted Einstein's equations in a project to visualize the black hole's inner anatomy. You could only get this close on a spaceship propelled by pure mathematics. Passing through the event horizon, we approach the central zone. As we whip around, we are flung out of a kind of cosmic tunnel known as a wormhole. At its end, we pass through what's known as a white hole. Like characters in a science fiction story, we exit into another time or place, perhaps another universe. This strange passage is the work of theory. In reality, it couldn't form amid all the turbulence.
The moment you introduce any real matter, then the stuff that's trying to fall in tends to collide with the stuff that's coming back out again. There's a turbulent, chaotic maelstrom deep down inside the black hole.
In a waterfall, this collision zone is where water crashes on the rocks and ricochets into the downward flow. Here, turbulence rises. All order disappears. In a black hole, the collision zone is the inner horizon, where swirling matter envelops the central core. That's the end of the line for a starship. It gets instantly vaporized.
The chief characteristic of this region near the inner horizon is that streams of energy are passing through each other, and they're passing through each other very rapidly. That counterstreaming of material begins to build up to the point where it self-gravitates, and that gravity accelerates those streams even faster through each other.
In the gentle world we know, the energy released by gravity quickly dissipates. Whatever crashes down settles into a state of rest. Inside a black hole, the energy does not dissipate. Instead, it builds on itself, rising to an extreme state known as the Planck density. To grasp what that is, imagine taking all the matter we can see with our telescopes, all the trillions upon trillions of stars that make up all the galaxies in the universe, and crush it
down to the size of a marble. No, don't stop there. Keep going. Crush it all the way down to less than the size of an atom. That is a Planck density. And that's the kind of density that is produced inside a black hole. It's the most extreme place in our universe outside the Big Bang.
In this state, temperatures rise to 1 trillion times hotter than the center of our sun. It would be hard to imagine what destructive impact the release of this energy would have. Fortunately, extreme gravity holds it tight within the black hole's event horizon. As astronomers project the continued evolution of our galaxy, they ask, will the matter and energy impounded within its central black hole remain there forever? Or is the black hole, like all other cosmic bodies, somehow subject to the ravages of time? We live at a time in which most of the energy of the universe is produced by stars. Trillions of years from now, all across the universe, stars begin to use up their fuel and fade away. The largest stars fall toward the centers of galaxies, where they're swallowed by supermassive black holes. As the universe decays, it gives way to a long era dominated by the remnants of dying stars and black holes.
The far future of the universe is one where the stars have burnt out and formed neutron stars or white dwarfs and some black holes, and eventually, over long periods of time, the black holes merge together to form bigger black holes.
In time, much of the matter within galaxies will fall into these black holes, and they will become the last bastions of our universe. How long will they last? The answer may come from a theory proposed by the cosmologist Stephen Hawking.
Stephen Hawking applied quantum physics to black holes and predicted that they wouldn't be black but would glow with heat radiation in a very distinctive way. And of course, if there's heat coming off, heat energy coming off, this energy has to come from somewhere.
The energy, Hawking said, would come from tiny particles emerging from the vacuum of space just outside the event horizon. Some of those particles radiate away, taking minute amounts of mass from the black hole, like water evaporating from the ocean. Over time, the radiation grows stronger and stronger as the black hole shrinks and finally explodes. When the last black hole dies, that's the end of the universe as we know it. How can we know if the theory is right and they actually do decay?
If black holes were made in the Big Bang with a mass of about that of Mount Everest, these black holes ought to be going pop about now, and radio astronomers have looked to see if they can see a sort of electromagnetic pulse associated with that. They haven't found any.
There might be other ways to see a black hole decay. From all across space, black hole jets are blasting particles out at very near the speed of light. These particles, called cosmic rays, slam into our Earth's atmosphere with enough energy to create miniature black holes. These mini monsters would decay immediately in a shower of particles, but they are very difficult to observe.
We're almost to store. The emittances look good.
Okay.
What if you could produce collisions this powerful in an Earth-bound lab and under controlled conditions actually create a black hole?
All right, so let's go ahead and
If you could then watch it decay, It would provide a unique window onto the future of black holes.
Okay, filling blue.
So we'll start collimating in blue ring.
It's hoped that taking two very high-energy small pieces of a very fast proton and colliding them with each other, you can put enough energy into a small enough space that you can actually create the conditions by which a black hole would form. These black holes are supposed to be very small, therefore very hot, and therefore they essentially radiate themselves away immediately.
1.2, 1.3, 10 to the 9.
Barbecue is still locked. Feedback looks good.
All right, here we go.
At Brookhaven National Lab in New York State, physicists are using advanced technology to blast gold atoms in opposite directions down giant tunnels almost 2.5 miles long. They accelerate these atoms to within a tiny fraction of the speed of light. When the atoms collide, a fireball erupts. Sophisticated sensors record a splatter of subatomic particles, a hot soup of gluons and quarks.
What we believe we're creating is temperatures approaching 2 trillion degrees centigrade. That's 100,000 times hotter than the interior of the sun. It's hotter than a supernova explosion. It's hotter than the surface of a black hole. It's hotter than a neutron star. In fact, we believe nowhere in the universe is at that temperature. It was last that temperature in the universe 1 microsecond, 1 millionth of a second after the Big Bang.
It's as if they are running the universe in reverse, taking us back to an instant when it was extremely hot and dense. Creating a black hole, it seems, will take even more energy than that. In fact, more than any Earth-bound collider can pack. That is, unless there's more to our universe and to gravity than we've thought.
Our injection efficiency looks good. The orbit looks good. Orbit RMS is under 2 millimeters in each plane.
Einstein's theory of general relativity is the one that we find in all the textbooks, and it's the one that we're all sort of pledged to defend, but it would be rash to say it's the last word on the subject of gravitation. And there are certainly alternative theories around, and some of them are quite popular. And some of these theories, these are non-standard theories of gravitation, predict that you could make a black hole by colliding together subatomic particles.
Some scientists believe they may be able to create one at a new and more powerful system in Europe called the Large Hadron Collider. The key lies in whether the world we know is part of a more complex cosmic reality, beyond the 3 spatial dimensions plus time that we experience in our everyday lives. If so, we would be like insects living on the 2-dimensional surface of a pond, unaware of the deep and complex reality below it.
That we can be living on the surface of the pond, happily minding our own business, but not realizing that underwater, something, say a fish underwater, could be swimming through the water, causing disturbances that propagate up to where we are. We could feel it happening, we could essentially see our universe around us changing, but we look around for the cause of it and we won't know what it is.
The idea is that a number of extra dimensions actually intersect our world.
10, 12 pi.
Okay.
When particles collide at very high energies, those extra dimensions enhance the gravitational force between the particles, enough to create a micro black hole.
Let's look good.
The scientists will know a black hole is there when they see the shower of particles predicted by Hawking's theory.
Ready to inject.
And for a moment, that will open a window to a deeper cosmic reality. The very idea that we could tap into this underlying realm shows how rich black hole research has become. Einstein's theory showed how black holes can generate extreme energies, cause the universe to wobble and bend, and twist up into knots. The recognition that black holes are fundamental to the workings of our universe is a major discovery of science in our time. And if it turns out that they do have a finite lifetime, their death will signal the end of our universe. By some estimates, the time horizon of the largest black holes goes out to a Google years. Take a 1 and add 100 zeros to it. That's an unfathomable spread of time, but it's far short of forever. The clock may well be ticking on our universe. The alarm will sound when the last black hole explodes.